A single modern AI server can have hundreds of gigabytes of memory. Some large AI models run on machines with terabytes of GPU memory, which sounds reasonable until you look closer, because the model itself often fits in far less memory than that. So what's exactly filling all that GPU memory? Is it just parameters, or is it the transformers architecture, or is something else happening inside the computation? Because the real reason AI models need so much memory is not what most people think. It's not just storing the model, it is the process of computing the answer. Let us start with the explanation that most people assume. Large AI models contain billions of parameters. Each parameter is simply a number, and every one of those numbers must live in memory. So the size adds up quickly. For example, a 70 billion parameter transformer model stored in FP16, which is 16-bit floating point precision, needs roughly 140 gigabytes of memory just to hold the weights. That alone already explains why these systems require powerful GPUs with massive memory. But here's where things get interesting, because if you perfectly fit those AI model weights into memory, the system still needs far more memory to actually run the model. Sometimes 2 to 5 times more. So something else must be occupying the memory. And that something is invisible if you only think about parameters, because the real memory consumer appears during the computation. Imagine a single token entering a transformer model. Maybe the word hello. The token enters the first layer. That layer processes it, but it doesn't just produce a final answer. It produces a tensor, a multi-dimensional block of numbers representing the token's internal representation. This tensor is called an activation, and every layer in the model creates one. A transformer may have 40 layers, 80 layers, and sometimes even more, which means every token generates dozens of intermediate activations. But here's the critical detail. Those activations cannot simply disappear because the next layer needs them. So they must stay in GPU memory while the computation continues. Layer after layer, token after token, the model is constantly producing intermediate data. It is temporarily but enormous. And suddenly, the memory footprint grows. Not because the AI model is stored, but because the AI model is thinking. Now we arrive at the part where memory usage explodes. And the culprit is the core idea behind the transformers: self-attention. Self-attention sounds simple. If you want to learn self-attention itself, you can watch this video. We are not going deep into the technical of self-attention in this video. Every token looks at every other token in self-attention. But that tiny sentence hides a dangerous mathematical reality, because comparing every token with every other token creates a matrix. If you have 100 tokens, the model computes 100 times 100 comparisons. That's 10,000 relationships. But if the sequence grows to 1,000 tokens, the matrix becomes thousands times thousands. That's 1 million relationships. And the model must store that attention matrix in memory, which means memory grows roughly like sequence length to the power of 2, quadratically. Double the context length, but memory increases 4 times, which explains something strange you may have noticed. Why increasing context length in AI models is so expensive? Why running longer prompts suddenly fills GPU memory? Why large batch sizes cause models to crash? Because the attention mechanism inside transformers quietly creates massive matrices, invisible temporarily but devastating for memory usage. Now imagine training the model instead of just running it. Everything we described so far was inference. Training is much worse, because during training, the system cannot discard intermediate values. It must remember them. Why? Because later it will run backpropagation. The backpropagation is the algorithm that calculates gradients and updates the weights, which means the model must store the activations, the gradients, the optimizer states, all of them in memory. And suddenly the memory demand multiplies. A simple rule engineers often remember is this: training typically requires 3 to 6 times more memory than inference. So that 140 gigabytes AI model we mentioned earlier, training it might require hundreds of gigabytes or even terabytes of memory, not because the model grew larger, but because the learning process creates layers of extra data around it. Now, this leads to another question. If AI models need so much memory, why not simply use normal computer RAM? Why do AI servers use expensive GPU memory instead? The answer is bandwidth. AI computations move enormous amount of data between memory and processors. Constants, activations, attention matrices, gradients, all flowing through the system them at incredible speed. Normal DDR memory is simply too slow for this workload. But GPUs are something different. High bandwidth memory, or HBM. HBM stacks memory vertically. It is closer to the processor. Therefore, it can move data dramatically faster, which is exactly what transformer models require. Because AI is not just compute heavy, it is memory movement heavy. And without that bandwidth, the GPUs would spend most of their time waiting for data. Because memory is such a bottleneck, engineers constantly search for ways to reduce it. Some techniques shrink the model itself. For example, quantization, which stores weights with fewer bits. Other techniques reduce intermediate data. The KV cache avoids recomputing attention during the generation. If you want to learn KV cache, you may watch this video. Some architectures, like mixture of experts, activate only a fraction of the model. And some training tricks, like activation checkpointing, recompute data instead of storing it. Every technique trades compute for memory, because memory has become one of the most expensive resources in AI. Not the GPUs, not the compute, but the memory surrounding them. So here is the surprising truth. AI systems do not need huge memory just because AI models are big. That's only the beginning. The real reason lies in the computation itself. Intermediate activations, attention matrices, gradients, temporary data created every time the model processes the text. Which means the model is not just storing knowledge. It is constantly building enormous structure of data while it thinks. And that's why the future of AI hardware may be shaped less by computing power and more by memory architecture. Because in modern transformer models, thinking takes memory, lots of it. Until the next video, good morning, good afternoon, good evening.